Now let's talk about subtraction with fractions. If we're dealing with like fractions, then it's pretty straightforward. We start out with a certain number of shaded parts and we remove a certain number of shaded parts. So if we started off with 2/5 and we're asked to remove one of those 2/5, then basically we visualize our 2/5 with one of them being canceled out. And then think about what's left over. There would just be one left over if I started off with 2 and I took one away. Because the pieces are already the same size, we don't have to do extra work here to find a common denominator. The same is true no matter what visual we use. In fact, the generalization looks a lot like the addition generalization. If we're adding a fraction, sorry, not adding, but subtracting a over b, and I want to subtract a fraction with the same denominator but a different numerator, then I would just copy my denominator over and subtract the numerator parts, and we're done. If, however, we're looking at unlike fractions, fractions with different denominators, we see the same dilemma that we saw when we were trying to add fractions with different denominators. We're not talking about the same size pieces anymore. So although we could still copy over our 2 yellow pieces and then remove an orange piece, you can see this is the orange piece that was removed. The problem is what's left is something that I don't know how to describe because the 2 pieces that I see are different sizes. If they were the same size, this would be fine. So we treat this the same way we did with addition. We have to find a common denominator. We divide each of our circles up into a total of 12 pieces. That's because between the denominator of 3 and the denominator of 4, that's what matches. And then when we transpose that onto our solution, we can see that there are 12 pieces for the circle and exactly 5 of them are shaded in. And we can do the same thing with the other 2 visual representations, the rectangle and the number line. We would just have to divide everything into the right size pieces, and then we can see that the answer would be the same. It would be 5 out of 12. Now that we've seen some of the visual representations for adding, subtracting fractions, let's do some of the examples where we don't have visuals or we don't want to draw the visuals. Visuals are useful for building a foundation of knowledge, but we can't draw pictures every time we want to do a mathematical calculation. That would be too cumbersome. So let's think about adding fractions with the same denominators. Maybe we're looking at something like 4/7 plus 3/7. Same denominator, great news, we just add them together. 4 plus 3 on top, copy over our denominator. That would be 7 out of 7. If you get a fraction where the numerator and the denominator match, you should definitely simplify. 7 divided by 7, or 7 parts out of 7 pieces needed to make a whole, that's 1 complete set. Sometimes it might happen that when you add 2 fractions, you get more than 1. Maybe we're looking at 6/7 plus 5/7. We would do 6 plus 5 for our numerator, copy over the 7 in the denominator. We know that 6 plus 5 is 11 out of 7. Now this is an improper fraction. And when we're dealing with improper fractions, sometimes we would like to leave them this way, and sometimes we don't. So you really have to analyze the situation. Is it better to talk about how many pieces I have that are that size, or am I trying to get a better feel for what this number looks like? Visualizing 11 pieces that are 7 necessary to make a whole, it's hard to grasp what that actual value is. We're better with comparing to whole numbers. So although an improper fraction is useful for calculations, we might want to turn this into a mixed number. Now, 11 out of 7. If I took 7 of those pieces and separated them off from the rest of the 11, that would leave 4 pieces in the the proper fraction part. So I can take that 11 out of 7 and separate it into a whole set and the proper fraction. And then I can write that as the mixed number. I have one whole set, and then I have the proper fraction 4/7. Now something to understand is that the fraction 11/7 is the same value as 1 and 4/7. Now 1 and 4/7, I know that that's a number between 1 and 2. So if I were on a number line, I know I'm somewhere in here. The fraction 11/7 takes a little more thought to realize that we're larger than 1 but smaller than 2. I know that 7/7 is equal to 1, and I know that 14/7 is equal to 2. So 11/7 is somewhere between 1 and 2. So each of these representations is useful, but sometimes the application calls for one versus the other. What about adding fractions with different denominators? Maybe I have the fraction 2/15 and I want to add that to the fraction 4/21. Just looking at these, we know that they don't have the same denominators. And I can find a common denominator by multiplying 15 and 21. And if we pull out a calculator, we'll see that 15 times 21 is equal to 315. So it's totally fine to use that as our denominator. Remember that I would need to multiply the first numerator by the second denominator. So that would be 2 times 21. And I would need to multiply the second numerator by the first denominator. That would be 4 times 15. That's just using the formula to do it. And if we clean up that numerator, 2 times 21 plus 4 times 15, that gives me 102 over 315. Now this is a correct answer. The problem though is that most of the time simplification is the best way to go. So anytime you add fractions together, or anytime you work with fractions, it's a good idea to see if it's possible to reduce it. Is this answer simplified? We can check on a calculator, but sometimes it's more of a hassle to pull our calculator out than it is to try and do it by hand. So what we could do is check to see if there's any common divisors. If the numerator and the denominator have a common divisor, then I can just divide it out. Now I can see that the numerator is even, the denominator is odd, so I know that 2 cannot be a common divisor. However, I do remember some of the tricks that we learned from Chapter 4 about determining if numbers are divisible or not by common factors. So I can check to see, is 3 a common divisor? Adding up the digits in the numerator, I get 3. Adding up the digits in the denominator, I get 9. 3 divides 3, 3 divides 9, so 3 is a common divisor. So we can divide that out right away. If I divide 102 by 3, I get 34. And if I divide 315 by 3, I get 105. If I wanted to check, is this simplified? All I need to do is look at the factors of 105 and look at the factors of 34. 105 might be easier to factor because I can divide it by 5 right away. 5 times 21. 21 only has 2 factors, that's 3 and 7. Since I can quickly find the divisors of 105, my recommendation is check to see if 34 is divisible by 5 or 3 or 7. If it is, then we found another common divisor. If 34 is not divisible by any of these, then we know that we're in simplified form. We know that our rules from chapter 4 say that 34 does not divide evenly by 3. That's because the digits 3 plus 4 add up to be 7, and 7 is not a divisor, not divisible by 3. Sorry. Next we can check 5. The rule for 5 says the number has to end in a 0 or a 5. 34 does not end in a 0 or a 5, so I know 5 does not divide 34. And then lastly, we need to know, does 7 divide 34? Well, the rule for 7s was a little tricky, so instead let's just think about our multiples of 7. We have 7 times 1, 7 times 2, 7 times 3, 7 times 4, 7 times 5. In fact, 7 times 5 is 35, so that's a pretty good clue that 7 does not go into 34 because it goes into 35. So we can see that they have no common divisors left, which means yes, this is simplified. Simplified answers are the best answers, so always take your time to see if you can simplify. And remember that you can check to see if you simplified correctly by seeing that you have equivalent fractions. So if you did 102 over 315, it should be true that that's equal to 34 over 105. Multiply through by your denominators, you get 105 times 102, and that's equal to 34 times 315, and we can check that on a calculator. 105 times 102 is equal to 10,710. And then 34 times 315, that's equal to the same, 10,710. So we definitely reduced our fraction correctly, and we know it's simplified because the numerator and denominator have no common divisors left. Now, it's true that we did not use the least common multiple for this problem, so I want to show you how a least common denominator can make this slightly faster. It's not going to be a substantial difference in most cases, but in some cases where the denominators are very different and they don't have any common factors, you're not going to see a huge difference. If they have a lot of common factors, you will see a huge difference. So let's find the least common denominator. Essentially, the least common denominator is the least common multiple of the denominators. LCD is the shorthand way of saying least common multiple of the denominators. So we just need to find the least common multiple between 15 and 21. We learned how to do this in chapter 4. Factor 15 down to its prime factors, that's just 3 times 5. Factor 21 down to its prime factors, that's 3 times 7. The least common multiple needs to contain one factor of 3 because each number has a 3. But then it also needs a 5 from the 15 and a 7 from the 21. Whoa, I wrote 7 instead of 3 for that first factor. So 3 times 5 times 7, that is our least common denominator. That product comes out to 105. And what do you know? That is the denominator that we got when we simplified our fraction. So if we had used our least common denominator, then what we do is multiply up each fraction to make equivalent fractions. So 2 over 15, we need to write an equivalent fraction with the denominator of 105. So 15 to 105, I just need to multiply by 7. So 2 times 7 for our numerator, that would be 14 over 105. And then the 4 over 21, to get the denominator of 105, I need to multiply 21 by 5, which means I need to multiply 4 by 5. I have 20 for my numerator. Now that I'm dealing with like fractions, I copy over my denominator, add my numerator, 14 plus 20, which gives us that same answer that we got before, 34 over 105. Now I get this question a lot. What is the easier way to do it? What's the best way to do it? Well, if you noticed, we're doing the same work, just in different orders. Using the least common denominator, you're shooting for simplifying your fractions first and then adding them. Using a common denominator by multiplying the two denominators just says get a common denominator and then simplify after. So you're doing the same amount of work, you're essentially doing the same type of work, just in a different order. Let's go through a few more of those unlike fractions. How about 2 over negative 3 plus 1 over 5? 2 over negative 3, we could write that as negative 2 over 3, or we could write that as negative 2 over 3. The representation of where the negative is quite unimportant, but I'm going to use the negative in the denominator, mainly because that's what your textbook is doing, and I want to try and align that with the textbook. So 2 over negative 3 plus 1 over 5, the first thing we need is a common denominator. I can see that 3 and 5 have no common multiples, so our best bet here is to multiply the 2 over negative 3 by 5 over 5. And I'm going to multiply the 1/5 by negative 3 over negative 3. That way I have a common denominator of negative 3 times 5, or negative 15. And then in the numerator I have 2 times 5, which is 10, and 1 times negative 3, which is negative 3. And then that gives us a final answer of 7 over negative 15. Now, although our problem started with a negative in the denominator, that is not the typical convention. So when your answer comes out that a negative is in the denominator, you should take one extra step to rewrite it, either as negative 7 over 15, where the negative is out front from the fraction, or put the negative in the numerator so that it's less of a chance that the negative could be overlooked. When we have the negative down here in the denominator, sometimes we don't see it. It's weird, but sometimes we don't see it. When the negative's out front or on top, it's more prominent, so less likely that we'll miss it. What about if we are trying to add 3 fractions together, like 3/4 plus 1/5, and then I want to add to that 1/6. Now in this case, the problem in the book actually has parentheses around these two, so we would add the first 2 fractions together. We need a common denominator. 4 has factors of 2 and 1. 5 has factors of 5 and 1. So they don't have any common denominators. We're going to multiply them by each other's denominator. So we'll have 3 times 5 plus 1 times 4 for the numerator, and then 20 in the denominator. 5 times 4 is 20. And then I'm going to carry down that third fraction so that I can do that when I'm ready. Simplifying the numerator in my parentheses, I have 15 plus 4. That becomes 19 over 20. And then I want to add to that 1 over 6. Again, they do not have the same denominators, but rather than multiply 20 times 6, I'm going to notice the fact that we have 2 times 10 for 20 and 2 times 3 for 6, which means that my LCD should be 2 times 10 times 3, which would be 60. 19 over 20, if I want to turn that into a fraction with a denominator of 60, I need to multiply top and bottom by 3. And the fraction 1 over 6, if I want to turn that into a fraction with a denominator of 60, I need to multiply that by 10 over 10. Then I'll have 19 times 3 plus 1 times 10 on top over 60. (19 times 3 plus 10 is 67. and 60 is our denominator. Now again, this answer is perfectly fine. It's an improper fraction, but sometimes it's worth converting that to a mixed number, so I'll go ahead and do that. 60 over 60 plus the remaining 7 pieces over 60. That would look like 1 and 7 over 60. When you do this process of converting to a mixed number, it's important to check that your fraction part is a proper fraction and that it is reduced. I know 7 over 60 is reduced because 7 is a prime number and 60 is not a multiple of 7, so they have no common divisors. Now just for practice here, if instead of having 67 over 60, if I had 127 over 60, I did some addition problem, I got 127 over 60. If I tried to take off just one whole, I would have to see what 127 minus 60 was. That'd be 67. Notice that I would have 1 and 67 over 60, and that remaining fraction is not proper, so I would need to continue to break that down. And maybe we notice that here when I split off 60 over 60, I still had 67 over 60, which means I have enough to do another whole plus the 7 that are left over. So 60 plus 7, that makes up the 127. So this one would end up being 2 and 7 over 60. Let's step out on the edge here and add together two fractions that have different denominators that aren't even numbers. X and Y are placeholders for some type of number. We do not know what X is. We do not know what Y is. They could both be the number 7. One could be the number 3, the other could be the number 5. We have no idea. In fact, X and Y could possibly have common factors. But because we don't know anything about them, we cannot assume that they do have common factors. So in this case, we're definitely going to multiply the two denominators to create our common denominator. And remember, with that pattern, I would multiply the 3 from the first fraction to the denominator of the second fraction. And I would multiply the 4 from the second fraction to the denominator of the first fraction. Just because we're using letters here as placeholders for numbers, it doesn't actually change the process. It actually simplifies it because we don't have to go through the lengthy process of finding a least common denominator. We use the only possible common denominator that we can think of. And then from there, we can't simplify this because we don't know what X and Y are. So we're not able to reduce anything in our numerator. We can't even add together those terms because they're not like terms. So this one's done. And if you think about it, a lot of us get a little bit weary when we see letters in our math problems, but this problem, start to finish, was like 2 steps. The other problems that only had numbers filled up the entire screen. So these ones might be a little bit easier. Let's see another one that has letters in it that might feel intimidating, but once we go through it, we'll see that it's not that bad. We have 2 over a squared times b plus 3 over a times b squared. We've got two denominators. One of them has 2 factors of a, 1 factor of b. The other one has 1 factor of a, 2 factors of b. Now if these were numbers, it would be something like 2 times 3 and 2 times 3 times 3. Now we don't know what these numbers are, so we can't go any further than that, but we can see that they both have a factor of a factor of b, but then the first denominator has an extra a, the second denominator has an extra b. So our least common denominator needs to have the a that they have in common, the extra a from the first denominator, the b that they have in common, and the extra b from the second denominator. So our LCD is a squared b squared. We're going to write these as equivalent fractions with the new denominator. So 2 over a squared b. If I want to turn that into a denominator with a squared b squared, notice that I'm missing a factor of b. So I'll multiply by b on top and bottom. That will turn that into 2b over a squared b squared. The second fraction, 3 over a b squared, it's missing a factor of a. So I'll multiply by a over a. That would become 3a over a squared b squared. Once they're like fractions, all we need to do is add the numerators and copy over our denominator. And remember, we can't simplify this because the numerator is a sum of two terms that cannot be combined. So there's no way to simplify it. This is done. So even if we're working with letters instead of numbers, we're still going to find a common denominator. If possible, we're going to try and reduce that denominator by grouping together common factors in the denominators. But in any rate, we're still using the same process of finding a common denominator and adding the numerators together. What about if we wanted to change a mixed number, like 4 1/3, into an improper fraction? Remember that we would just multiply our denominators, multiply the denominator to the whole number, is what I meant to say, and then add the original numerator to that, and then copy over the old denominator. So that would be 13 over 3. Or maybe we have a negative number, 3 2/5. Now something to recognize here is that this negative out front is saying that the entire number, the entire mixed number is negative. It's not just the 3. It's not saying the whole number is negative and the fraction is positive. It's saying the whole number is negative and the fraction is negative. So when we multiply, we would have the denominator times the whole number, and then I'm going to subtract the numerator, the original numerator, because it's a negative 2/5, not a positive 2/5. That would look like negative 15 minus 2, or negative 17 over 5. What if we wanted to take a mixed number and improper fraction and turn that into a mixed number? Well, if I have 39 pieces, essentially what I'm doing is finding out how many whole pieces I can make. I know that 39 can be written as 5, my denominator, times 7. 5 times 7 is 35, plus 4. So if I can take my numerator and rewrite it using that division algorithm, I can see that it looks really similar to how we took a mixed number and turned it into an improper fraction. So now we're going to reverse it. 5 times 7. 5 was the denominator, so I know I'm going to keep 5 as my denominator. If I'm multiplying 5 by 7, then 7 had to have been the whole number part. And then the 4, that would have been the numerator. So 7 4/5. If we wanted to, we could draw a picture. 39 pieces and coloring in the 1/5 at a time, and we would see that we'd complete the whole 7 times, and we'd have 4 pieces out of 5 left over. When it comes to adding mixed numbers, essentially you can think of it as that you're adding the whole number parts and then adding the fraction parts. So if I'm adding a number like 5 1/3 to the number 2 3/4, I could look at it as add the whole number parts, 5 plus 2, and then add the fraction parts. It's 1/3 plus 3/4. And then once I've added those parts separate, add those results together. 1/3 and 3/4, we've actually worked out similar problems to this. We know we need a common denominator. It would turn out to be 4 plus 12. Just kidding, 4 plus 9 over 12. Adding 4 and 9 together would be 13 over 12. So the fractions combine to give me 13 over 12. The whole number combines to be 7. Now, this isn't totally incorrect, but it's not a proper answer because the fraction is improper. When it comes to writing a number as a mixed number, you should always simplify the fraction part and write it as a proper fraction. 13 over 12 is actually 12 over 12 plus 1 over 12. Because our fraction has a whole inside of it, we would add that to the whole number part in the mixed number. So 7 and 13/12, that looks like 7 plus 1 plus 1 over 12, which is 8 and 1/12. Now what if we were to subtract these two fractions? This can actually pose a bit of a challenge. When it comes to subtracting mixed numbers, we're often tempted to compute it the same way that we did the addition, where we group the whole number and then we group the fraction part. If we do that, we would still add the whole number to the fraction part, but be very careful of what happens here. 5 minus 2 is 3, not a big deal. 1/3 minus 3/4, that would become 4 minus 9 over 12. And now that we understand negative numbers, we know that 4 minus 9 is equal to -5. So if our whole number is positive, but our fraction is negative, we're a bit in trouble. There's two ways to remedy this. We could say 3 minus 5 over 12. And in that case, we would need to turn the 3 into a fraction. And then we would need to turn the 3 into a fraction with a common denominator. Then we could subtract 5 over 12. 36 minus 5 is 31. That's 31 over 12. And since we started off in mixed numbers, we should probably write our answer in mixed numbers. I know 12 can go into 31 twice, because 12 times 2 is 24. If I take that 24 out of the 31, I would have 7 pieces left over. So the mixed number would be 2 and 7/12. Another way to do the same thing is to immediately recognize that the fraction parts are going to result in a negative because 1/3 is smaller than 3/4. And when you subtract something big, you get a negative. So what we can do is borrow from the whole number 5. So 5 and 1/3, we can write that as 4 plus 1 and 1/3. I can turn the 1 and 1/3 into an improper fraction, which would be 4 over 3. So if we looked at it as 4 and 4/3 instead of 5 and 1/3, we can remedy this issue of having a positive whole number and a negative fraction. So 5 and 1/3 minus 2 and 3/4. Let's think of that as 4 and 4/3 minus 2 and 3/4. We'll group together the whole numbers. We'll group together the fractions. We'll subtract our fractions. Oops, I ruined my denominator. This would become 16 minus 9 over 4. That would be 7 over 4. And then the whole numbers, 4 minus 2 is 2. So it'd be 2 and 7/4. Oops, not fourths. I needed the common denominator. 3 times 4, 12. And we get the same answer, 2 and 7/12, 2 and 7/12. So again, which way is easier? That's going to depend on you and the way that your brain likes to think. So pick which one works best.